The concurrency number sitting in your scraper right now probably came from nowhere real. Somebody picked 20 threads, or 50, or just cranked it up to whatever the proxy pool could technically push through, and shipped it. That number tells you what your own servers can handle. It tells you nothing about what the target site can handle, and those are two completely different ceilings. The second one is the one that actually decides whether your requests come back as clean data or come back as errors, challenge pages, and silence. Get that number wrong and you don't find out slowly. I run proxy farms for a living, dozens of servers, hundreds of mobile and residential exit points, feeding scrapers that have to run every single day without getting the whole range flagged. I've watched concurrency settings turn a clean pipeline into a wall of 403S in under an hour. And I've watched the same target handle triple the load at 3 a.m. that it choked on at 2 p.m. This isn't theory. It's what I deal with when a client's scraper stops returning data and I have to work out whether it's my proxies or their pacing. Here's the thing most people miss. Every response the target sends back carries more than just the payload you wanted. It carries timing. It carries a status code. Sometimes it carries an explicit rate limit header telling you exactly how long to wait. Sometimes the failure itself has a shape. A timeout is different from a connection reset, which is different from a block page served with a 200 status like everything's fine. All of that is the target side of a conversation, and the scraper that ignores it is running blind. Sites don't publish their real capacity anywhere. There's no page that says we can absorb 200 concurrent connections from a residential range before 3 a.m. and half that after. The only way to find the actual ceiling is to watch what comes back while you're pushing load and adjust in real time instead of trusting a number you picked before you'd sent a single request. A site that's fine at low load during a quiet stretch can start serving degraded responses the moment a traffic spike from real users hits at the same time your scraper is running. The earliest warning sign is almost always latency creeping up under load that used to be fine. If the median response time on an endpoint starts doubling or tripling as you add concurrency, that's the target's infrastructure, or a load balancer in front of it, or a WAF doing heavier inspection, working harder to keep up with what you're sending. Latency drift shows up before outright blocking does, which is exactly why it's worth tracking on its own instead of waiting for the error rate to move. In practice, that means keeping a rolling window of response times, say the last 100 requests to a given host, and watching both the median and the 95th percentile inside that window. If the 95th percentile climbs past some multiple of its steady state value, say double or triple what it normally sits at, that's your cue to cut concurrency for that specific host rather than push through it. Pushing harder into rising latency almost never fixes it, it just piles more queued connections onto both ends of the conversation. Status codes are the most direct signal a target ever sends you, and they each mean something specific if you actually read them instead of just checking for a 200. A 429 is about as unambiguous as it gets. The site is telling you directly that you're over the rate it's willing to allow. That should always trigger a backoff. It should never trigger a retry at the same rate because you already know what happens the second time you send that same load into a wall that just told you to stop. A 503 usually means the origin, or something sitting in front of it, is shedding load, and it tends to show up specifically under heavier concurrency and disappear again once you drop back down. Some 503 responses come with a retry after header attached, and that header is the target literally stating in plain terms how long you need to wait before trying again. That's not a suggestion to root around. It's an instruction, and honoring it is the difference between a scraper that recovers gracefully and one that digs itself deeper. A 403 that starts showing up intermittently correlated with how much volume is coming from a given IP or sessions usually means a WAF or a bot detection layer has decided that source looks suspicious and started challenging or blocking it. From the outside, watching your own error logs, a rising 403 rate at a given concurrency is a hard ceiling. It's the target's automated defenses doing exactly what they're built to do, and there's no clever pacing trick that changes a decision the site's own security layer has already made about that source. Captchas and interstitial challenge pages are the same story from a different angle. When a site starts serving a challenge instead of the content you asked for, that's the site actively protecting itself from a traffic pattern it's classified as abnormal or automated. The correct read on that, from an operator's chair, is that it's a stop signal, not an obstacle to engineer around. Continuing to hammer a target that's already decided your traffic looks automated doesn't change its mind, it just burns more sessions and gets more of your IP range flagged for nothing. Below the HTTP layer entirely, there's a whole other set of signals worth tracking separately. TCP resets, refused connections, playing timeouts where nothing ever comes back at all. A target that starts silently dropping connections instead of returning any status code is often doing coarser blocking, sometimes right at the network edge rather than inside the application. That tends to show up once concurrency from a single IP or a narrow range of IPs gets high enough to look like one unusually aggressive client rather than normal traffic. If your scraper only checks the status code on a response object, it never even sees a connection that failed to complete. So track that failure rate on its own. Concurrency limits don't exist by themselves, they're tied directly to how the proxy layer is set up. And this is the part a lot of scrapers get backwards. The exact same total volume of requests looks completely different to a target depending on how it's spread across sources. 100 requests a minute coming from one data center IP looks like a single very active, very suspicious client. Spread that same 100 requests across a rotating pool of 20 different residential or mobile IPsIN, it looks like 20 separate ordinary users, because that's genuinely what that kind of traffic normally looks like on those ranges. Data center ranges are the easiest thing in the world for a site to fingerprint and block as a block, because they sit in well-known, well-documented ASIN ranges that any halfway competent detection system already has a list of. Residential and mobile ranges look like ordinary consumer traffic, because that's what they physically are, carrier-assigned or ISP-assigned addresses that naturally see a regular bursty use from real people. That changes what concurrency even means at the target end. 5 requests a minute from each of 20 residential IPs reads completely differently to a rate limiter than 100 requests a minute from one address, even though the raw volume is identical. None of that changes what the underlying signal means. A 429 is still a 429 no matter what kind of proxy sent the request that triggered it. What it changes is where you apply the fix. Sometimes the real constraint is total concurrency against the target overall. Sometimes it's concurrency per individual source, and widening the pool while keeping per IP load low solves what looks like a hard ceiling without touching total throughput at all. The target's error rate at each configuration you test is genuinely the only reliable way to tell which one is actually the constraint you're up against. So here's how I actually set the number in practice. Start low, run a small fixed concurrency against the target, and just record 2 things: baseline latency and baseline error rate before you touch anything else. Then step concurrency up gradually in small increments, watching those same 2 numbers after every step. There's almost always a point where latency and error rate stay basically flat for a while, request after request, and then start climbing sharply rather than gradually. That's the number you're actually looking for. Picture what that actually looks like on a real target. You run 10 concurrent requests and see a median latency of 400 milliseconds with basically 0 errors. So you step up to 20, then 30, then 40, watching the same 2 numbers after each step. At 30, concurrent request latency is still sitting close to that 400 millisecond baseline. At 40, it's suddenly sitting at 1200 milliseconds, and you're seeing your first scattered 503s. That jump between 30 and 40 is the inflection point on this particular target, on this particular day, and it's the number the target just handed you for free if you were watching for it. That inflection point is the real ceiling, and it is not the same thing as the highest concurrency that technically still returns 200 responses. Running right at that edge is dangerous precisely because it leaves you no room, the very next small spike in the target's own load, something that has nothing to do with your scraper at all. A traffic surge from real users, a deploy on their end, anything pushes you straight past it into block territory with 0 warning. A sensible operating concurrency sits comfortably below that inflection point, not right up against it, paired with an automated backoff that fires on any of the signals already covered, a 429 response, a rising 503 or 403 rate, latency crossing some threshold above baseline, or a jump in connection failures. The backoff itself needs to actually reduce concurrency, proportionally, not just pause for a few seconds and resume at the exact same rate that triggered the problem in the first place, because resuming at that same rate just triggers the same response again. Some signals mean the target simply doesn't want this pattern of traffic at any concurrency, and the honest answer at that point is to stop, not tune the number further. Repeated CAPTCHA challenges that keep showing up even after you've backed off, a robots.txt file that explicitly disallows the path you're requesting, terms of service that prohibit automated access outright. These aren't rate-limiting problems that better pacing solves. Concurrency tuning is for staying gracefully inside a target's technical capacity. It was never a way to get around a target's stated policy on being scraped at all. And no amount of careful signal reading changes the answer to that second question. A scraper that actually respects a target's own feedback, instead of running a static number picked on day one, ends up producing better data anyway. Fewer retries eating your budget, fewer blocked sessions you have to recover from and rebuild, and a pipeline that's still running next week instead of getting an entire IP range flagged and burned this week. None of this makes a scraper invisible or guarantees it never gets blocked. Nothing does that. It just means the blocks that do happen are the target's genuine policy decisions rather than self-inflicted damage from ignoring signals that were sitting right there in every response. I run the proxies behind real scrapers myself. The full written guides and the proxy setups I actually use are at proxyscraping.org. And that's also where I break down how residential, mobile, and data center ranges actually test against real targets instead of just taking a provider's word for it. Full written guides and tested proxy picks at proxyscraping.org. Go take a look and subscribe if this kind of thing is useful to you.